For this lesson, we're going to take all of the work that we've been doing with regards to limits, and we're going to start to put it into practice. And we're also going to put it into practice in a way that gives us a result that's much more practical than constantly taking these limits. But we do have to start with limits. And so just to remind you, when we talk about, for example, the slope of a tangent line, if we want to know the slope of the tangent line at a particular value of x, let's say x equal a, the way we do that is we take a following difference, so f of a plus h minus f of a divided by h. So what I have here is simply the slope, and then I ask myself, what happens to that slope as h gets vanishingly small, as it approaches 0? This is the derivative. So as you can see here, nothing new. All I've done is gone from referring to the slope of the tangent explicitly and just calling that the derivative. And I'm using this new notation. So if we started with the function f of x, now we have what's known as f prime, and f prime is the derivative. So in this case, f prime of a is the derivative of f of x when x is equal to a. So the prime part, the little hash mark here, that's the prime, that means derivative, and then of course it's still the same function notation. We also, when we talked about limits, we did introduce an alternate notation. Instead of saying that h approaches 0, what you can actually do is you can just say that the denominator is x minus a, but as x approaches a, then the difference between x minus a is going to become vanishingly small. In other words, it's going to approach 0. So these two are equivalent expressions. There's no difference between them. Sometimes we prefer to use one over the other because one might be more convenient than the other, but they are absolutely equivalent forms when it comes to expressing the rule for a derivative, which is the exact same rule for the slope of the tangent, which is the exact same rule for the instantaneous rate of change. Now we are going to be focusing on one particular derivative for this lesson, and that derivative is summarized as the power rule. So if I start off with my function f of x in a very particular form, so if f of x is in the form x, so the independent variable x, raised to some exponent, and the only restriction here is that my exponent has to be some sort of real number. So it can be a whole number, it can be an integer, it can be a rational number like a fraction, or it can even be a decimal. So if that's the case, then f prime of x works out to be n times x to the power n minus 1. So the rule here to apply it is when you take the derivative, you take whatever's up here in the exponent and you multiply by it. And then you take whatever's in the exponent and you subtract 1. That's your new result. And this f prime of x is the derivative, but it is also the slope of the tangent. It is also the instantaneous rate of change. Now this is going to give us a method that allows us to come up with exact algebraic expressions for derivatives, and we're not going to stop here with the power rule. In future lessons we're going to go beyond that. And so for example, we're going to take a look at these examples down here. We're going to apply the power rule to them and show that we can come up with the derivative for these in a far simpler way than trying to apply our rules for limits. Some of these we could have done using limits. Actually, all of these we could have done using limits. But there's a lot more work involved in doing so. Okay, so let's go ahead and try these out. Now before we actually dive into them, a couple of side notes that I want to make very quickly. There are different notations that you may see for derivatives. So I wish I'd put this first. F prime of x is going to be the one that we focus on, but this prime notation is also going to appear sometimes if we've got the function just written in terms of y. So for example, if we just have something like y equals x cubed, then we might be interested in the derivative, which would be y prime is equal to, and then we would figure that out. In this case, the derivative would be 3x squared. I took this number 3 down in front, so it became 3 in front, and then I subtracted 1 from the remaining exponent. So that's y prime. Then we have dy by dx. Same idea here. We start with y equal x cubed, and then dy by dx just means take the derivative of y with respect to x, with respect to the independent variable. And so once again, we would end up with 3x squared. F prime of x, now that would mean that we're defining f of x equal to x cubed. And then we have this one, the Leibniz notation. And this is one that is actually, it's the most powerful of all of the notations here, but it's also the one that students find the most difficult to get comfortable with. So I'm mentioning it here, but we're not going to spend a lot of time looking at it. Now, some of the rules that go along with derivatives, we've looked at some of these rules with respect to limits, and it's actually very similar. So the first one is, if we're taking the derivative of a constant doesn't change. So that means that essentially the instantaneous rate of change of a constant is 0. The derivative of a constant is 0. The power rule itself, which we've already looked at, if f of x is equal to x to the power n, then f prime of x is n times x to the n minus 1. If we have our function multiplied by some constant out in front, then when we take our derivative, that constant remains unchanged. We just ignore the constant, we leave it as a multiplier in front, and we take the derivative of the function itself. If we have the sum of two functions, so if f of x is defined as g of x plus h of x, then when I take the derivative, I just take the derivative of each of the two individual functions individually, and the sum remains the same. I'm still adding them. And if I have a difference, g of x minus h of x, then when I take the derivative, I just get g prime of x minus h prime of x. There is a similar set of rules that goes along with using Leibniz notation. And as you can see just from looking at it here, Leibniz notation is more complicated seeming, but as I mentioned, it is much more powerful. Okay, so let's get back to those examples that I put down earlier. And I would recommend at this point, it's a good point to pause and maybe give these a try yourself. So I'm going to do A and B on this page, and I'll do C and D on the next. I do give you a hint here, which is to express all the terms as powers of x. So this first one, so I'm going to go ahead and start with these now. This first one is already expressed as individual terms in powers of x. So, and it's in a y notation. So this one I'm just going to go ahead and write it as y prime. So I'm going to take the derivative, I'm going to call it y prime, and I'm going to apply that individually to each of these, because all we have here are sums and differences of different functions. If it helps you to think of it, you could define this one as f of x, this one as g of x, this one as h of x, and then you would take each of those individual derivatives. So you know what, since I've written these out, I'll do that separately. So if f of x is equal to 3x squared, then what's f prime of x? I take this 2, I bring it down in front, that becomes 2 times 3 is 6, times x, and then x to the power 2 minus 1 is equal to 1. And of course, that's just equal to 6x. G prime of x, I started with 5x, so now I have a 1 here, I bring that down, that's still 5, and then I have an x, and then this is x to the power 1, but I subtract 1, that ends up being x to the power 0. But x to the power 0 is simply equal to 1, so g prime of x is just equal to 5. And finally, we had h of x, which was equal to 7, so that means h prime of x is equal to 0, because the derivative of a constant is equal to 0. Now we could have done this all in one shot. This is the only time I'm really going to break out and look at these individually for such a simple function. So we have 3x squared becomes 6x minus 5x, the derivative of that is just 5. And then the other one is just 0. We don't bother showing that. So the derivative of this is 6x minus 5. Now this is useful. This is telling me that if I want to know the slope of the tangent or the instantaneous rate of change at any value of x, so if I wanted to know that at x equals 3, I would just sub x equals 3 in here, and that would tell me the slope. Okay, let's move on. Give you some time to digest that, to think about that. We're going to write this one as individual terms of x. So the way I'm going to do that is I see a difference of squares here. So I'm immediately going to write that as x squared minus 16. And then I will expand that out. So I end up with y equals x cubed minus 16x. And now I can take my derivative. I'm going to show an alternate notation for the derivative on this one, which is dy by dx. And it's the same thing as y prime. Dy by dx, the derivative of y with respect to x, is going to be equal to, the first part gives me 3x squared. I bring the 3 down, times x, and then 3 minus 1 is equal to 2. Minus 16x to the power 1. I bring the 1 down. That's still 1 times 16 is 16. But x to the power 1, 1 minus 1 is equal to 0. This becomes, right here, this becomes x to the power 0. But x to the power 0 is simply equal to 1. So that becomes 3x squared minus 16. Now we want to express all terms as powers of x. For part C here, we've got 5 over x squared. Preferable to write this as 5x to the power negative 2. We always want it in that form, f of x equals x to the power n. So we don't want something in the denominator, we want it in the numerator, or just along the regular line of the expression. So y prime is equal to, it's going to work the same, except for the introduction of the negative is going to complicate things a little bit. So now we have a negative 2 coming down in front, so negative 2 times positive 5 is negative 10 x, and now negative 2 subtract 1 is actually to the negative 3. We could leave it this way, or we could return it to the form that the question was originally given to us and see it that way. So this became negative 10 over x cubed. But that's perfectly fine, and that's fine, certainly for now. Finally, this one, this is a square root. So once again, I'm going to write this as powers of x. So the first thing I'm going to do is I'm going to take 2x cubed, and I'm going to instead write it as the square root. I'm going to write that to the power 1/2. 2x cubed to the power 1/2 is the same as 2 to the power 1/2 and x cubed to the power 1/2. So what I've done is I've applied this square root to each of those terms individually. This 2 to the power 1/2 just stays out in front, so I can actually rewrite that back as square root of 2 now. And I could have started that way as well. And then x to the 3 to the 1/2 is the same as x to the 3/2. And now I'm ready to take my derivative. So once again, I'll use that alternate notation. dy by dx is equal to, this number in front just stays the same, that's square root 2. And then I bring down this 3/2 x, and now I subtract 1. 3/2 minus 1 is actually 1/2. And now I'm going to simplify this. This is just a number. This is just a number. So I actually end up with 3 root 2 over 2 as I bring those together. And x to the 1/2. This is a perfectly good way to write this. Or you could write this as 3 root 2 over 2. And then x to the 1/2 is the same as square root of x. And if you were going to go this far, I actually wouldn't want you to stop at this point. If you're going to bother writing this as square root of x, I would write that as 3 times the square root of 2x, combining those, over 2. So this one or this one would be acceptable. Okay, so there's some practice with the algebra of the power rule. For this exercise, we'll be putting this into practice. We've been asked to find the point on the curve, so we're trying to identify where on the curve is the slope of the tangent equal to 0. So what we're asking, we're saying where is the slope of the tangent equal to 2? I said equal to 0, sorry. Where is it equal to 2? And that's the same thing as saying, where is f prime of x equal to 2? Or in this case, since we have xy notation, we want y prime. So that's what we'll start with. We're going to start with y equal x squared plus 2x minus 3. We will take the derivative using the power rule. So the derivative of x squared is 2x. The derivative of 2x is simply 2, and the derivative of the constant negative 3 is equal to 0. So we end up with y prime equal to 2x plus 2. This is an algebraic expression that describes the slope of the tangent at any x. So what we want to do is we want to set y prime equal to 2 and then solve. So we end up with 2 equal 2x plus 2. Subtract 2 from both sides, we end up with 0 is equal to 2x, or x is equal to 0. So we end up with the slope of the tangent is equal to 2 at x equals 0. Alright, so let's get a visual representation of that. And to do that, we're also going to need to graph this. Now this is in standard form, so it has a y-intercept of negative 3. So I'm going to put on a scale here, negative 3, and I have a point there. It might also be useful for us to put this into, for example, factored form. And so in factored form, I can do that in my head. Two numbers that multiply to negative 3 and add to negative 2, that's going to be x plus 3 multiplied by x minus 1. So that means I'm going to have one of my zeros is here at positive 1. Another one of my zeros is over here at negative 3. And from here we can actually see quite clearly that my axis of symmetry is halfway in between at negative 1. And if I put negative 1 in here, I actually end up with 1 minus 2 minus 3 is equal to negative 4. So we end up with our vertex down here at negative 4. And by symmetry, we would have another point here. So I end up with my parabola looking something like that. And what I found was that the slope of the tangent is equal to 2 at x equals 0. So I think for that I want a straight line. At x equals 0, well, that's this point right here. And what I found is that the slope of the tangent is equal to 2. It's not perfect, but we end up with that straight line. And if you take a look at my, let's just try to get that a little bit better. And if you take a look at, for example, each one of these, here I've got each square is half, so 2 squares is 1, so that's over 1, and then 3, 4, so that's plus 1 in the x direction, plus 2 in the y direction, so that is a slope of 2. And a little interesting aside here, that actually comes from, when we're in standard form, this middle term, in case you've ever wondered, the value of this middle term is the slope at the y-intercept. So this value of negative 3 was the y-intercept, and the slope of this tangent is equal to 2 at that y-intercept. And that's it.